Hello everyone and welcome to today's video where we will talk about meteorology, and more specifically we have prepared 6 questions from the topic of winds. So we will talk mainly about low level winds. However, there will also be a question regarding the turbulence and the mountain waves. So without any further ado, let's jump into this very simple, however tricky at times topic. So for question number 1, the reported surface wind for Brussels airport located in Belgium is 250 degrees and 9 knots. What is the expected wind at approximately 2,000 feet AGL? So of course, this question asks us about our knowledge of the surface winds and how they change, so either veer and back and speed up or slow down with altitude. So generally speaking, 2,000 feet is the mark, up to 3,000 depending on the question, where the friction force will stop affecting our winds, and below that altitude, this is where these surface winds will prevail. Of course, the rule of thumb is quite simple. There are 2 cases that you need to know for the exams. One is over water and one is over land. Over land, the wind will be backing as you go down by 30 degrees and the wind speed will drop by 50%. And over sea, it will also back as you go down, and the direction will back by approximately 10 degrees and the speed will drop by approximately 70%. The reason for that is that water and oceans and sea, of course, is much less rough than land, so the friction is less. In this case, the situation is reversed, so instead of going down, we'll be going up. So the wind will not be backing, it will be veering in the northern hemisphere. So of course, when the wind is veering from 250, we're going clockwise, meaning by 30 degrees. Now the wind will be blowing from 280 degrees, and now the wind will be faster by 100%, because of course it is halved as we go down, so it needs to be double as we go up. And this means that our wind now, as we are exiting the friction level, will be 280, blowing at 18 knots. So just for practice, if this was the case over land, we would be talking about 260 as we go up 260 degrees, and stronger by the 70 knots, 70%, sorry. So in that case, it will be approximately 14 knots. For question number 2, so you are flying from east to west in the northern hemisphere at 500 hectopascal pressure surface. Which of the following statements is correct? So this question can be very simply answered using the Bouy-Ballot's law, meaning when wind is blowing at our back, the low pressure area is at our left. So first of all, we need to know whether we're flying towards the low or high pressure area. In the question, you can see that the wind is either blowing from south or north, or headwind or tailwind. If we have headwind or tailwind, that means we are flying directly between low and high pressure areas and systems. So this doesn't really make much sense for the sake of the question, as in that case, the pressure would be relatively constant as we're flying parallel to the isobars. In that case, we need to consider the 2 scenarios, either from north or from south. So when the wind is blowing from the north, this means that when the wind is positioned blowing towards our back and we're flying east to west, that means we are flying from low pressure zone to high pressure zone. And you need to remember, it is very easy to use mnemonic: high to low, watch out below, meaning when flying from high pressure to low pressure, your true altitude decreases, although your altimeter reading might be the same. In this case, we are flying from low to high, meaning our true altitude will actually increase. So as you can see, the first question, if the wind is from the north, we are gaining altitude. This is because we're flying from low to high, so our true altitude is constantly increasing. Now for question number 3. So wind speed in case of a gradient wind is. And this is a great opportunity to just quickly recap all 3 most important winds when it comes to low-level winds. These will be, of course, the geostrophic wind, which is the most basic one. The geostrophic winds will take into account our pressure gradient force, as well as the Coriolis force. For geostrophic winds, remember that because geostrophic force is used to divide, it can never really be 0. So geostrophic winds we can really take into account only above around 15 degrees above the equator, and this will be conversely proportional to the latitude. If to this geostrophic model we add centrifugal force, which has to do with the curvature of the isobars, then we have the gradient wind. And this gradient wind will be stronger as this force, the centripetal force, is added on top of the pressure gradient force. So now the pressure gradient force together with the centripetal force will be opposing the Coriolis force. And lastly, of course, the surface winds, which essentially adds to the whole equation the friction force. And as we discussed before, an easy estimation was 70% over water, 50% over land, 30 degrees over land, and 10 degrees over water. As we go up, the wind is veering. As we go down, the wind is backing in the northern hemisphere. So going back to the question, wind speed in case of gradient wind is dependent on the curvature of the isobars, because this adds to the equation the centripetal force, which has to do with the wind turning around the low and high pressure systems. And now for question number 4, and this is actually a question that we can already answer by knowing and using what we just discussed in the previous one. So at the same latitude, the geostrophic wind is less than the gradient wind around an anticyclone with equal pressure gradient, because the centrifugal force is added to the pressure gradient. And this is absolutely true. It is added to the pressure gradient, because otherwise it would be opposing the pressure gradient force, and it would not be added. It would not increase the wind. It would decrease the wind. Of course, the centrifugal force alongside the pressure gradient force will be opposing the Coriolis force only. And now for question number 5. So an aircraft is flying in the southern hemisphere at low altitude, less than 2,000 feet, and going directly away from a center of low pressure. What direction relative to the aircraft does the wind come from? So one thing that the examiners are trying to catch you here on, of course, is that we are talking about the southern hemisphere. So in the southern hemisphere, when it comes to anticyclones, the wind will be going clockwise. This is, of course, mirrored in the northern hemisphere, so the exact opposite. So now, as we are flying along the pressure center of low pressure, the wind is going clockwise, and we are flying away. And now, of course, the wind, because it's going clockwise, it will be hitting us from the left side. Now the question is whether it will be coming slightly from the tail or from the nose. And here, of course, the situation is the same as in the northern hemisphere, because the wind always goes from high to low, meaning if we're flying away from the center of low pressure, we need to be flying towards a position or a place of higher pressure, meaning now we're flying towards the wind, so that we'll experience some form of slight headwind. So the answer will be from the left and slightly on the nose. And now for question number 6, so the last question of today's video. Name the most important conditions for the formation of significant lee waves within a mountain range. So this is also a very practical question, as these phenomena are extremely dangerous and important to be identified before your flights. Always, if mountain waves, lee waves, or standing waves, because they have many names, if they are discovered, they will always be shown in a SIGMET, so make sure you cross-check these charts before your flight. The main conditions for these wings to be created is the wind has to be at least 15 to 20 knots. It needs to be always perpendicular to the mountain range. The good allowance is plus minus 30 degrees, especially for the questions. Remember, the direction of the wind can be plus minus 30 of the mountain range, however, not more. And lastly, there needs to be a stable level approximately at the height of the mountain top. And these mountain waves can go as far as 50, 150 nautical miles and create rotors. And above them, there can be lenticularis clouds, which indicate the presence of these lee or mountain waves. Extremely dangerous. These can reach speeds of 2,000 feet per minute on average, however, sometimes much, much more, all the way up to the tropopause. This is why they cause moderate to sometimes even severe turbulence and big threat to flights, and definitely a discomfort. The stability here, remember, is because the mountain waves, although they are like waves in a sea, they always kind of go down. And if there was complete instability, in this case, the waves wouldn't be created. The air would simply just escape and go up and do convection activity, potentially creating storms. If there is a stable layer, these parcels of air are essentially bouncing off the top and bottom, creating these waves. So of course, here for these questions, you always need to look for perpendicular and stable conditions, as these are the most important prerequisites for the Lee waves to be created. And of course, in this case, answer Charlie, a strong large-scale wind increase up to levels and blowing approximately perpendicular towards the mountain range under stable thermal stratification. And this will be everything. So thank you so much for joining. I hope this was helpful, and I hope we'll see you in the next video. Best of luck with your exams. Bye-bye.